Morning, everybody. Let's go with some green checks if you can hear me. We might be missing a few people. Has Mrs. Wood stopped teaching this morning, or is she still going in homeroom? Want to fill me in there? Got green checks. She's done. Perfect. Thank you, Ava. Few things I'll mention while the last few people kind of trickle into class here. I split up Unit 5 into kind of two parts, kind of make smaller chunks for you guys to look at. So I asked you guys finish that first part yesterday, and then a few of you had some questions that we kind of left with. So I wanted to kind of answer those. So if you didn't get it in yesterday, if you can get it in today, that would be great. Because by the end of today's class, we'll be 2 lessons into kind of the second half of that Unit 5. So in the class behind me here, Lesson 5, Learning Guide Part 1, due Tuesday. So that was yesterday. A few of you had questions that we left off with. I think it was Abby was asking about the Learning Guide, and this was on page 4, number 4, and it said, define domain and range in terms of words, number line, a list, set notation, and interval notation. So I just wanted to kind of clarify that I went over all of these, maybe except number line, and I looked into the lesson in the course, and this is what it ended up looking like. So words is pretty self-explanatory up here. That's just words. The domain is between 2 and 7 sort of thing. Number line, pretty straightforward, close dot, open dot sort of thing. A list, we didn't use list for all of them, but a list is good for discrete points. So if you had something that wasn't a line, but it was just unique points, then you could use a list like that. Set notation we used, except we used a bit of a different notation. We just included the like x is less than or equal to 5, and we didn't include this bit or this x and then the line. So we did the set notation, and then interval notation we did as well. So I guess the only thing I didn't cover was the number line, but you guys have seen number lines, and hopefully that's nothing too shocking. So I wanted to go through that. As well, Taylor, you had a question. I think you asked about the circle one in the learning guide. And we did one really similar to it in the lesson last day, so I'm hoping you figured that out. Is there anything else from there that anybody wanted to go over? Anything I didn't cover? Anything you're confused about, perhaps? Nobody? Somebody? Okay, perfect. So, yeah, if you handed it in just what you had done, that's fine. I can appreciate that some of these things can be stuff that you weren't aware of how to answer or whatnot. So that's that. I'll jump back to lesson 3. Kind of left at the end of the class. And then there was this one water tank question. So I can go through it real quick just because I didn't and it's there, so we might as well. It leads really nicely into what we're going to do today, so we might as well look at it. And anyway, so a water tank on a farm near Swift Current holds 6,000 liters of water. Graph A represents the tank being filled. Graph B represents the tank being emptied. Identify the dependent and independent variables. All right. So the independent variable in both of these examples is going to be time, because time is independent. And the dependent variable is the volume. So it depends on, the dependent variable depends on how much time, what time you're asking about. If you're asking about, like 10 minutes, 20 minutes, then I can tell you what the volume is. So it's kind of dependent on that. So we have these two graphs and a few questions regarding them. So let's kind of, my questions, of course, are got cut off. All right, so determine the rate of change of each relation, then describe what it represents. So rate of change is the change in each of the variables. And we kind of described it as the rise over the run or the slope of the line. So let's take a second to kind of figure out what the rate of change is. So the first thing we need to do is find the change in our volume. And you'll notice on our graph, we've got a couple points drawn in here. There's a point there, and a point there. So we just kind of pick any 2 points we like. Maybe we'll pick these 2 points over here. The reason I use the points that are on the line is because I don't really know what this is here. I'm going to have to estimate something like that. So instead of using an estimation, I can just look and say, okay, that crosses a grid point and that crosses a grid point. Those are 2 points I know. So up here my volume is 4,000 and down here my volume was 3,000. So if I'm looking at those 2 points, the change in volume, it's going to be 4,000 minus 3,000. So I end up with 1,000 liters. That's my change in volume. I also need to know the change in my other axis, so the change in time. So what 2 points was I dealing with? Well, I started here at this 4,000, which was at 80 minutes, and then I looked at the 3,000, which was at 60 minutes. So my change in time is going to be 80 minutes minus 60 minutes. So the change here is going to be 80 minus 60, which is 20 minutes. So that means every 20 minutes my volume changes by 1,000 liters. So when I talk about the rate of change, I'm not interested in talking about the change over 20 minutes. I'm always interested in figuring out what the change is over one of whatever the kind of horizontal or x-axis represents. So if in this example we're changing each minute, I want to know the change per minute, not the change for 20 minutes. In this case, it's 1,000 liters every 20 minutes. I want to know the change for 1 minute. So what I do is I find the rate of change. And a quick way to write this is rise over run. And in this example, we had a rise of 1,000 liters divided by a run of 20 minutes. 1,000 divided by 20 should end up with 50 liters per minute. So the rate of change is 50 liters every minute. In this case, the rise, we were talking about going from the point here up, and then our run over here. So this rise was 1,000, and this run was 20. So 1,000 divided by 20 ended up giving us 50. And in this case, we're talking about liters per minute. So let's look at the second part here. Similar graph, except we're talking about the tank emptying now instead of filling. And you notice that instead of the line kind of going up and to the right, now it's going down to the right, so that the tank is losing volume. So I'm going to pick the 2 points again. In this case, let's look at these ones. So we're talking about a rise. Even though it's going down, we call it a rise still. And then a run is going across. So we need to find the rate of change again. So we're going to find our change in volume. So I ended at 2,000 liters and I started at 4,000 liters. So my change in volume is going to be minus 2,000 liters. So I've gone down 2,000 liters. I'm not filling my tank, I'm emptying my tank. And over what time span did that happen? If I look at my graph, I started my emptying at 20 minutes and I ended at 40. So it took 20 minutes to get that change in time. So the change in time is going to be 40 minutes minus 20 minutes. Which is equal to 20 minutes. Now, same idea as before, the rate of change is going to be the rise over the run. And in this case, we went down 2,000 liters in 20 minutes. So what's happening to our volume? Well, we're losing 100 liters every minute. So rate of change is the rise over the run. The first example, we were increasing or filling our tank, so our volume was increasing every minute. The second question, we were decreasing or emptying the tank, so we're losing volume every minute. Basically, you take any 2 points, you find the change in the vertical, and then you divide it by the same change in the horizontal. You just divide them. And the idea with rate of change is it's always per one. So it can be liters per minute, it can be dollars per hour, it's always divided by 1. Get out of the way on that side. Thank you. And as I mentioned, we're going to look at this a little bit more in depth today. One really, maybe an interesting thing, maybe not, I'm not sure what you want to call it. When I was in high school, I had a physics teacher. His name was Mr. Strawn. He was a physics teacher at KSS. And he ended up becoming a mentor of mine. When I graduated, I went back and I worked with him. And he taught me all he knew. But when I was in his class, he said, if you ever get a graph and you don't know what to do with it, find the slope. 99% of the time, when you're given a graph, some point, they're going to ask you what the slope of the line is, which is the rate of change. It's the same thing we just did. So that holds really true in this unit and the next unit we're dealing with. If you don't know what to do, find the slope of the line. We're going to spend tons of time talking about slope, and it's kind of interesting how these units lay out. So we're going to look a little bit about slope now, and then actually in the next unit, Unit 6, pretty much the whole unit we look at slope. So if you don't really strongly grasp it here, we're going to definitely learn a little bit more about it, or definitely see it again in the next unit. So the independent is time, the dependent is volume, Abby. So that kind of finishes up lesson 3. And like I mentioned, it's really similar to the stuff we're going to do today. So I figured we might as well take another look at it. So what we're going to do, if nobody has any questions about any of that stuff, I'm going to jump into lesson 4. And we'll just kind of go from there. So the title here is Interpreting Graphs of Linear Functions. Basically, we're just going to look at graphs, and we're going to try to get information from our graphs. So what can we kind of look at on the graph and figure out what's going on? So graphs are really powerful because they can give you a lot of information in a really small amount of space. The idea is, can you sort of decipher the information from the graph? What is the significance of each of the points? What is the slope of the line? What units we're talking about? And things like that. So any graph of a line that is not vertical represents a function. We call these functions linear functions. And we looked at the difference between linear and nonlinear functions last day. And hopefully you remember when we're talking about linear functions are exponents for x and y. If we look at the equation, they don't have anything greater than 1, so it's just going to be x and a y. If we're talking about nonlinear functions, our x or our y is going to have an exponent that is 2 or larger, or half, I suppose. So anything that's not 1 is going to give us a nonlinear function. So linear is kind of what it sounds like, a line. I know when we have a graph like this sort of thing, and we have a curve or a parabola, you're saying, well, that's a line, it's just a curved line. When we're talking about linear functions, we're talking about completely straight lines, even though that red line isn't completely straight, but gives you an idea of what linear functions are. So 2 examples of linear functions here. Let's kind of see if we can decipher some of the information here. Each graph below shows the temperature, T, in degrees Celsius as a function of time in hours for 2 locations. So we have temperature versus time. 2 different places. We don't know where the places are, but doesn't really matter, I guess. The first one here, temperature of location A. The point where the graph intersects the horizontal axis. So when we're talking about the horizontal axis, we're talking about right here. And if we wrote that as an ordered pair, what would that be? So an ordered pair is going to be our x term, and then our y term, and then we separate them with a comma. So if we're on the horizontal axis, our y value is going to be 0, because we haven't gone up or down. And our x value in this case is going to be 4. Taylor, you were right, you just got them backwards. We always go x first, then y second. So that is right, though. Got them mixed up. The horizontal intercept is, so if we're just asking where does it cross that horizontal axis, we're going to say 4. So just 4. And what is the significance of that point on this graph? Why do we care when it crosses that axis? What's the importance of that axis? If we were kind of going to interpret the information as to what's going on here, what's significant about the horizontal axis? To answer your question, domain is x and range is y. Yes, Alex, you got that right. And Abby, you're right. So it's 0 degrees. Why is 0 important? Well, our whole Celsius temperature scale is based on the freezing and melting point of water, which is 0 degrees Celsius. So we have a lot of water on our little blue planet, and that's an important sort of temperature. So the point of intersection represents, I'm going to be really specific here. We're talking about after 4 hours. The temp is 0 degrees Celsius. So the time at that horizontal point is 4 hours, the temperature is 0. There we go. So I was talking about the horizontal axis. Now we're going to talk about the vertical axis. And in this case, the vertical axis is representing temperature. And I just read that right off the graph. And where the graph intersects the vertical axis in this particular question is right down here. So where is that? Well, if I look, this is 0, this is 10, this is 10, this is 20. So each line on the graph represents a temperature jump of 5. So in the vertical, my x value is 0, and my y value is -5. So the vertical intercept, the place where the red line crosses the vertical or the up and down axis, that is at -5. Now, trying to figure out what's sort of significant about this point is maybe a bit trickier. because it might not be completely obvious. There's not a ton of significance to it, but the point of intersection represents what? What does that point, mean? It's saying, okay, at -5 is the temperature there. So the idea here is that we have to start our time somewhere. And when we started recording our time, the temperature was -5. So at 0 minutes or 0 hours or whatever, the temperature was -5 degrees. So that's just when we started, it was -5. And Abby, you're on the right track there. So we could just write something like the temp when we started was -5 degrees Celsius. All right, that's pretty good for that much. And domain and range, Alex was asking about this a second ago. Remember, the domain is all the x values we use. So if you think about it as being like a light bulb up above or down at the very bottom, it's going to cast shadows on that horizontal axis. So where are those shadows cast? What is the smallest x value we're using? What is the largest x value we're using? And all the points in between, because it's connected with a line in this case. And then the same thing for the y values. If you think about casting a shadow onto the vertical axis, what is the largest y value? What's the smallest y value? And of course, we're a continuous line between those, so where are we going to kind of fall in between there? So we just kind of looked at how many different ways there are to write domain and range. I kind of like using the interval notation. It's probably one of the most common ways you'll see these things written. So the domain is the x values, and the smallest x value looks like it's 0, and the largest x value looks like it goes all the way up to 12 here at the end. So my domain is going to be my x values, and it's going to be between 0 and 12. And then I need to think, okay, my x's are going to be all bigger than 0 and all smaller than 12. So I have closed dots at either end. So my x values are going to be greater than or equal to 0 and less than or equal to 12. I'm going to do the same thing with my y values. Looks like the largest y value I use is up here at 10. And the smallest is going to be at -5. So all of my y values fall between +10 and -5. So I know my range is my y values. My smallest is -5, my largest is 10. And going to be greater than 5 and less than 10. Now, one thing that I probably would change is the fact that I've used x and y here. In this case, the horizontal axis isn't measuring x's, it's measuring time, or lowercase t, and then the vertical axis wasn't measuring y, it was measuring temperature, or big T. So if you've written this down as the domain range like this already, that's fine. To make it perhaps a bit more correct, I would change my x and y. So my horizontal axis is measuring time. So my time is between 0 and 12. And my temperature, or big T, is between -5 and 10. So that would probably be a little bit more correct way of representing that. I forget who it was that asked why I wrote my T's like this. Now we're getting into something with a temperature and a time, and we could be adding those things together conceivably. So now we have temperature, time, and a plus sign. Crazy T cross sort of thing. So generally speaking, temperature is big T, time, little t, and then a plus sign just looks like a plus sign, and that way we don't get any of those things confused with one another. The last thing here asks about the rate of change, and we know the rate of change is equal to the rise of my line over the run. So we just spend a bit of time looking at an example of this. So the rise is going to be the change in temperature divided by the change in time. Ava's asking a question about if one answer on a quiz had the x and y and one had the t and other t. Generally speaking, you're not, I shouldn't say you're not going to, but you wouldn't probably see one like that. You'd always just have whatever the graph had on it. It wouldn't say x and y if the graph was measuring time and temperature. So you wouldn't encounter something like that, generally speaking. I think it was just kind of a lapse in concentration on my behalf. Okay, let's go back up to our graph. We need to figure out a change in temperature and divide it by a change in time. So we need to kind of pick 2 points on our line. And you can see that over here, they've already kind of done this calculation for us. They've found 2 points right here and right here. And they said, okay, what's the rise? If I go from my first point to my second point, how much did I go up? So it looks like they started at, they finished at 10 and then they started at 5. So you went up by 5 degrees Celsius. And then the run, how far across did I have to go? So it looks like I started at 12 and, started at 8, finished at 12 over 4 hours. So the rate of change is going to be 5 degrees every 4 hours. So that's my rise divided by my run. But I'm not interested in how much my temperature changes every 4 hours. I want to figure out how much it changes every 1 hour. So all I need to do is just divide these numbers. 5 divided by 4 is 1.25 degrees Celsius per hour. Or you could write it on top of one another, like that. So that's going to be your rate of change there. It's just simply doing the division. 5 degrees Celsius every 4 hours. How much is it going to change in 1 hour? Just 5 divided by 4. 1.25 degrees Celsius per hour. And it's positive, so that means the temperature is going up. And the graph kind of represents that because it's kind of going up and to the right. So the temperature is increasing as time goes on. Now, temperature in location B is almost the same question we did. It is the same question, except that the temperature is actually starting higher and kind of dropping down. So we're starting at, looks like 10 degrees, and then we're finishing at minus 10 degrees. So I want you guys to just have a go. See if you can follow the same process we just did for the horizontal intercept, the vertical intercept. See if you can figure out the domain, the range, and then most importantly, the rate of change. So the change in temperature over the change in time. See if you can pick 2 points. I think points are already indicated on the graph, so you just need to do the change in temperature divided by the change in time. So I'll give you guys maybe like, I don't know, 2 minutes or something. See how far you can go, and then I'll just run through the answers real quick. So good luck. All right. Hopefully you guys had a chance to get through at least one or two of those. I'm just going to kind of rattle through the answers real quick, and then if you have any questions or didn't get something that I wrote down, just fire it into chat, and hopefully we can sort it out. So the first part is asking for the horizontal axis. Where does it intersect? So I'm looking at in this case, the time axis, and I see that it intersects right here, halfway between 4 and 6. So if I wanted to write that as an ordered pair, I'd say x is 5 and y is 0. Horizontal intercept is 5. And then the point of intersection represents, just like we wrote on the other side here, in this case after 5 hours, the temperature is 0 degrees Celsius. So that was the first part. Second part was the vertical axis. The vertical axis we intersected at x is 0 and 10. The vertical intercept is 10, and that means our initial temp is 10 degrees Celsius. So when we started recording our temperature, we started at 0. The domain, what x values are we using? What's the smallest x and the largest x? So smallest x value is 0, the largest is 10. My x's are all between 0 and 10. And then my y values are all between negative 10 and positive 10. So I'm going to write it like that. So hopefully you can get up to that point. And then the rate of change was probably maybe something a little bit trickier. We haven't done a ton of these yet. So the rate of change again is going to be the change in temperature divided by a change in time. So I picked 2 points on my graph and divide them. So looks like a change in temperature. They've figured it out for me already, so negative 10 minus 0. So it looks like they're taking the point here and the point here. So my rise is, I'm going down by 10. So going down by 10, and then my run is going across, and in this case, it took 5 hours to go down those 10 degrees. So the change in temperature is negative 10 degrees Celsius divided by a time of 5 hours. So what's happening is we're going down 2 degrees Celsius every hour. And that is our rate of change. How did we do on that? Let's go with thumbs up, thumbs down. Maybe like thumbs up and down if you got some but not all. Did we do okay? What do we think? How are we feeling about x-intercept or vertical, horizontal intercept, domain range, rate of change? I have 1 thumbs up. If you can make it to the rate of change and get stuck, that's okay. So we haven't looked at a ton of the rate of change stuff yet, so we'll look at a few more. Ava Anna, forgot the negative. And one thing is, like I was saying, we'll look at so many graphs, eventually you'll just be able to look at a graph and say, oh, that slope's negative because it's going down. I'll get my hand gestures backwards. Alex So-So, Taylor's doing okay. Okay. Let's go to the back, and we'll look at a couple more examples here. We're going to spend a whole day tomorrow talking about function notation, and you can see it's actually kind of introduced here but it doesn't really probably make a whole lot of sense right now. So when we're dealing with functions, there's a special way of writing them. And this kind of gets back to the mathematical sort of language shorthand that mathematicians use for everything. And we'll just kind of, it pops up and we'll just kind of skirt around it, and we'll talk a lot more about it tomorrow. So we can use the intercepts to graph a linear function. We only need 2 points ever to graph a line. If it's going to be a linear function or a straight line, if you can have 2 points, you can always join those 2 points wherever they are with a straight line. So if we have 2 points, we can draw a line on a graph. So let's look at how we can do that. So to determine the y-intercept, we find the y value when x equals what? Let's just look at this blank graph for a second. If I want to figure out where the graph or my line, so my line's going to be like one of these guys, something like that maybe. If I want to figure out where it crosses this vertical axis, what are the x values of every point on this vertical axis? What does x equal here? If I haven't moved away in either direction from that vertical axis, the x value is always going to be what? What do we think? Any ideas? I just wrote it. Shucks. Abby's got it. Ava's got it. Let's look at a couple example points. I'm going to write them in red. Don't write this down. If I had a point right here, I wanted to write the ordered pair of that point. I'd say, okay, that's 0, 2. If I had a point down here, that would be 0, -1, 2, 3, 4, 5, 6, 7. If I had a point maybe way up here, that would be 0, 2, 3, 4, 5, 6, 7, 8. So no matter where I am on that vertical axis, the x value is always going to be equal to 0. So we're going to use that fact to determine what that y value is. So to determine the y-intercept, find the value of y when x is equal to 0. That is, evaluate this. This is called function notation. And we have f bracket x. If we were to read this, we would say f, the brackets is of, and then x. So if I were to say it, I would say f of x. I could have g, I could have h, I could have all sorts of other letters in there. It could be h of p or t of x. It's just function notation, kind of shorthand. So we say this f bracket x, we read that as f of x. F stands for function, yeah. And we don't always use f for functions. So if we have, maybe we're dealing with more than one equation at one time, we could have f and g and h, and those are just kind of the more common ones. But it can be anything, really. It could be t. Yeah. So when we have f of x, or our function, when x is equal to 0, or we can write it as f of 0. So all we're doing is replacing the x with 0. This function notation here, if it's not kind of super clear, don't worry about it. We're going to spend all of next day working on it. But the important thing is that if we figure out when x is 0, we can figure out what the y-intercept is. So let's do the same thing with the horizontal axis, or the x-intercept. So when we want to find the y-intercept, the x-intercept, we want our y to be 0. That is, determine the value of x when f of x equals 0. So all we're saying is, hey, just make y equal to 0, figure out what x is. So let's just look at an example. I'm sure I've confused you all with function notation. Here's a line. This is the equation of a line, negative 2x plus 7. Instead of writing it as f of x equals negative 2x plus 7, for simplicity's sake, let's just change it for now to y is equal to negative 2x plus 7. So you guys have dealt with equations in x and y before. That'll just make everything a little bit easier. So if I want to figure out the y-intercept, I need to make my x value equal to 0. So when x is 0, what does y equal? So I'm going to take my equation, y is equal to negative 2. And anywhere there's an x, I'm going to substitute in a 0. So y is equal to negative 2 times 0 plus 7. So this is 0 plus 7. Y is equal to 7. So what does that mean? Well, that means when x is 0, so if I had like an ordered pair, x is 0, y is equal to 7. So now I have a point that I can plot on my graph. So 0, negative, or near 0, 7. So I'm going to plot that. 1, 2, 3, 4, 5, 6, 7. I'm going to put that point on my graph right there. And that is 0, 7. That is my y-intercept. That is where my graph crosses the vertical axis. So that's 1 point. I can't plot a line yet with 1 point. I need 2. So I have to have 2. So now I'm interested in finding the x-intercept. Just like my y-intercept, when all of my points on that vertical axis, the x value is 0, same thing for the horizontal axis, except now y is going to be equal to 0. So I'm going to take the same equation, and I'm going to make it anywhere there's a y, I'm going to plug in a 0. So I get 0 is equal to negative 2x plus 7, just from the equation that I started with, the equation of my line. So what I'm trying to do is isolate my x value. So I'm going to add 2x to both sides. So I end up with 2x is equal to 7. Just continue over here. I get 2x is equal to 7. And then I'm going to divide both sides by 2 to get that x by itself. And I end up with x is equal to 7 over 2. So what does that mean? That means when my y value is 0, x is equal to 7 over 2. And if I'm going to plot it on a graph, I should probably write it as 3.5, because that's going to be a lot easier to find than 7 over 2. So I'm going to plot this point now. My y value is 0, so I know I'm going to end up on the horizontal axis. And in this case, it's 3.5. So 1, 2, 3.5. There's my second point. So I now have 2 points. In order to make a line, I can connect those 2 points. So I'm going to grab my trusty ruler, and I will connect my points. I missed. Let's try that again. It's a bit better. Now I've drawn my line on my graph. I'm just going to add a couple notes in here. So I'm looking at the y-intercept here. So if I want to find my y-intercept, I make x equal to 0 and then solve for y. And same thing down here for the x-intercept. I make y equals 0, then solve for x. So this is kind of a process that you're going to use to figure out what the line looks like. So what we've done here is we've taken this equation, y is equal to negative 2x plus 7. We said, I wonder what that looks like. So we said, okay, let's figure out where it crosses the vertical axis, and then we'll figure out where it crosses the horizontal axis. If I want to plot a line, I need 2 points. So in order to figure out where it crosses the vertical axis, I know my x value is always going to be 0. And when it crosses the horizontal axis, my y values are all equal to 0. So I've substituted in 0 there, 0 there. I solve, and I end up with this line. There's a bunch of questions similar to this in the learning guide, so you'll have some time to go over those. Example number 2 gives us 2 graphs, and it says the rate of change is 1/2, and the vertical intercept is 6. Which graph represents this sort of thing that we're kind of describing here? All right, so when it says the rate of change of 1/2 and the vertical intercept of 6, rate of change may be a bit more difficult to kind of visualize on a graph. So let's go for this, the vertical intercept. So where it crosses the vertical axis. In this case, it's saying the vertical intercept is 6. So let's look at both of the graphs and figure out if maybe one of them crosses that vertical intercept at a point that isn't 6. So we could just eliminate one of these graphs right away. So if I look at the first one, I see that it's crossed at 6, so that doesn't work. And this one is also crossing at 6. Okay, so they both cross at 6. So I've kind of ruled out the idea of them having a unique y-intercept. So they both cross at 6. So now I'm stuck with this rate of change